So on an exam or this specific type of problem on the quiz, if you have a question, will a precipitate occur? Okay, will it happen? You're going to have to compare KSP with Q. Okay, so in this, sorry. All right, we'll take 2 now. Okay, so if you see this problem on a homework or a quiz or a test, and it asks, will a precipitate occur? Okay, you're going to have to compare 2 things. Okay, you're going to have to compare KSP to Q. The problem that we left at last Wednesday, we have calcium hydroxide, and they tell you it has a KSP of 8 times 10 to the minus 6. So this is the KSP equation for calcium hydroxide. So this is something I want you guys to do. I want you to write this equation independently on your own. Okay, so you should know this. Okay, calcium hydroxide. I mean, I'll give you the formula for calcium hydroxide, though honestly you should also know that. But you should know that it's going to break down in a KSP to calcium ion plus hydroxide ion. Okay, a lot of students forget to balance. So we always want to balance our equation. So what's the formula for KSP? It's products over reactants. Calcium hydroxide solid is an example of something called a sparingly soluble solid. So sparingly soluble solids will have a KSP. In fact, if you look at page 12 of our notes, okay, there's a whole list of these. It's hard to see, so I don't mean for you to squint, but a bunch of KSPs from a bunch of solids that are sparingly soluble, which means they do this. They can go back into their ions. Right? So this is the equation. The KSP is products over reactants. Okay? So some of that solid calcium hydroxide will go this way, so that will be plus S. This will be plus 2S. We're going to put S here. We're going to put 2S squared there. And then we're going to plug in our concentrations of calcium ion and hydroxide ion. Okay, where did we get those? Okay, we got those from the concentrations after mixing. Okay, so this is how much hydroxide ion, and this is the total volume after mixing. Okay, same thing with the calcium ion. Okay, this is the concentration and the volume, and this is the total volume after mixing. Okay, so here the Na plus and the Cl minus are soluble in water, and we call that spectator ions. Do you remember spectator ions in Gen Chem 1? Okay, so they're not doing anything, they're just floating around in the water, but this is reacting with this to give you calcium hydroxide. Okay, so we figure out the concentrations, we plug them in here. If it equals to KSP, that means we're exactly at equilibrium. If it doesn't, that means it's going either towards the product side, or if it's not, if it does not equal to KSP, it's going towards the reactant side or the product side. So we need to calculate this and determine how it is related in relation to KSP. All right, so 2 times 0.000399. Okay, we'll square that times 0.0998. So we get 6.4 times 10 to the 8. Ten to the minus 8. And then what is our KSP here? It is 8.0 times 10 to the minus 6. So obviously they do not equal to each other. Okay, they do not equal to one another. So I'm going to put Q first. Okay, it's 6.4 times 10 to the minus 8. And the KSP, which we got from above, is 8 times 10 to the minus 6. Okay, so which is bigger, Q or KSP? KSP is bigger. It's bigger 100-fold, 100 times bigger. 10 to the minus 6 is bigger than 10 to the minus 8. It's actually 100 times bigger. And where do the alligator jaws point? The right. So will this precipitate? Okay, the answer is no. Okay, no. Okay, under this concentration and this volume of OH minus, sodium is spectator. And when you mix that with this concentration and this volume of calcium chloride, okay, the chloride is just a spectator. Okay, the calcium ion and the hydroxide ion aren't enough concentrated and aren't enough in volume to initiate a precipitation. Okay, the Gator rule tells us this. For the Gator rule, you always want to put Q first. Okay, you always want to put Q first. So, yeah, there'll be no precipitation here. Okay, that's not enough. Not enough. Okay. All right, so that's how we do these types of problems. All right. All right, we're comparing Q with KSP. All right, so that's page 11. And page 12, I know this table is hard to see, and I didn't make it for you hard to see on purpose. It's just that this is a list of sparingly or slightly soluble compounds, okay? The solubility products, okay? So all of these have KSPs, okay? So there's a lot of solids that can go back to their individual ions. Okay, and that is KSP. So, yeah, okay, I'll give you these values. You do not memorize them. You do not ever memorize them. You'll be given that to them, okay? So you guys know molar solubility, okay, moles over liter. Here, this is also known as concentration of a solution. Solubility sometimes is in grams over liter, okay? So sometimes we can express solubility in grams over liter as well. And some problems that we will do next will cover that. So let's go quickly to page 13. Okay, the idea here is to show you this table with all these different sparingly soluble compounds, and then solubility can be expressed in moles over liter, or it can be expressed in grams over liter. Here's another table that's pretty good to look at if you have it in your textbook, or I think if you print out the copy of your notes like Leslie has, you can probably see this better. But this is the KSP expression, and then the relationship, the math that you have to do. So this is good if you print it out because it tells you how to solve for S. Okay, S is the solubility. All right, so the solubility of calcium sulfate is found experimentally to be 0.67 grams over liter. Calculate the value of KSP for calcium sulfate. Okay, does anybody remember the formula for calcium sulfate? Okay, so that's the formula for calcium sulfate. And it tells you its solubility is 0.67 grams over liter. So we'll have calcium sulfate here as a solid is in an equilibrium with calcium ion plus sulfate ion. And are we balanced here? Yes, we're balanced. Oh, I'm sorry. I gave you the wrong formula for calcium sulfate. Okay, this is the formula for calcium sulfate. I was wondering what's going on here. So the formula for calcium sulfate is CaSO4. Okay, calcium is +2, sulfate is -2. So let's rewrite this again, because now I have the formula for calcium sulfate correctly. Alright, so the solid we don't care about, and this will be +S, and this will be +S. So the value of the KSP, so this is in a 1-to-1 ratio. So KSP is equal to calcium ion and sulfate ion. Okay, so this will be +S, +S. Okay. So KSP, so this is S, that's going to go in here. This S is going to go in here. Okay, so S times S is S squared. Okay. So this 0.67 grams over liter, that's a solubility. Let's convert that to moles over liter. Okay, and with that moles over liter, we can plug that in here to give you the KSP. Right? So that's the plan of attack for this problem. Okay, so this solubility that goes in here is moles over liter. So 0.67 grams over liter of calcium sulfate times 1 mole of calcium sulfate is how many grams of calcium sulfate? Get the periodic table here. Oh, perfect. Awesome, thank you so much, Asia. Alright, so calcium sulfate, calcium here is 40.07. Maybe 40.08. Sulfur is 32.06. Okay, oxygen is 16.01 times 4. So that's 64.04. Okay, because remember we have to multiply it by 4. So quickly getting us the molecular weight of this 40.08 plus 32.06 plus 64.04, 136.18 grams are in 1 mole of calcium phosphate. So 1 mole of calcium phosphate is 136.18 grams. With the grams cancel. So 0.67 divided by 136.18 gives us about 0.00492 moles over liter. Okay, moles over liter. And that's something, let's plug it in here, okay? As our S. KSP is equal to 0.00492 squared, and what do you guys get when you do that on your calculator? 2.4 times 10 to the minus 5, so 2.42 times 10 to the minus 5. Okay, so that is the KSP for calcium sulfate. Right, so that's how we solve for the KSP. The S that comes in here, the solubility, is in moles over liter, concentration. Okay, do you remember this if I use brackets? Okay, do you remember this if I use brackets? That brackets means moles over liter. Okay, what is the solubility of silver chloride in grams over liter? I think we did this already, but we'll do it again. AgCl is in an equilibrium with Ag plus, aqueous plus Cl minus, aqueous. All right, some of that will go this way, so this is a solid, we don't care. Plus S, this is just like the calcium sulfate in our previous problem. KSP is equal to Ag plus times Cl minus. Okay, so we got an S that goes in here, we got an S that goes in there. 1.6 times 10 to the minus 10 is equal to S squared. So solubility S is equal to the square root of 1.6 times 10 to the minus 10. And what is that on our calculator? One 1.26 times 10 to the minus 5. Okay, units are molar. Okay. So because it's 1-to-1, the solubility of silver will be 1.26 times 10 to the minus 5 molar. The solubility of Cl minus will be 126 times 10 to the 5 molar. Okay. It's a 1-to-1, so let's convert it to grams over liter by putting it in, by multiplying by the molecular weight. Okay, so this is what I mean. Moles of AgCl in 1 liter times 1 mole of AgCl. What's the molecular weight of AgCl? 107.86. And Cl is 35.45. About 143.31 grams are in 1 mole of AgCl. So the moles cancel, and then we'll go with grams over liters. Bless you. 0.00181 grams over liters. So 0.00181 grams of Ag plus will go this way if you're precipitating 1 liter of solution, or if you have 1 liter, and 0.0018 grams of Cl minus will be dissolved per liter if you're making 1 liter of precipitate, or if you have 1 liter of solution. Okay, so usually we go with molarity, like on the exam. You don't have to do this step, but in some cases there'll be problems where they ask you the solubility in grams over liter, but I'll ask you the solubility in terms of moles over liter on the test. Okay. All right, so I need to get do this. I need to get the KSP out for the problem in chapter page 13. So just give me 2 minutes. I'll give you guys a 2-minute break here because we need to get the KSP value. So I'm going to go grab that in my big book here. We're back. Hope you enjoyed your break. All right, so here we go. Here's that question again. Will a precipitate form? Okay, so what two variables will you compare? KSP and what? Okay, Q. Okay, Q. Okay, actually, we put Q first in the Gator rule. Will a precipitate form if exactly 200 mLs of 0.0040 molar barium chloride are added to exactly 600 mLs of 0.0080 molar potassium sulfate? Okay, so this barium chloride is in the form of BaCl2 and Cl minus, and this one in solution is K plus and SO4 minus 2. So this potassium ion and this chloride ion are spectator ions. They will not precipitate anything. They will not be involved in the reaction. So actually this barium and this sulfate will react and form a solid. But is this enough? Is this enough and this enough to give you a solid? And that solid being barium sulfate. All right, so this is the equation that happens. Barium sulfate is in an equilibrium with barium ion plus SO4 minus 2 ion. Okay, so this is where I had to grab my book here, and I want to tell you guys the KSP for barium sulfate is 1.1 times 10 to the minus 30. Okay, it's a very, very small number. So that's the KSP that we are dealing with here. And this is the KSP for barium sulfate, the sparingly soluble solid. All right, some of it will go this way, and it will go this way, and what goes this way would be plus S. What goes this way also would be plus S. All right, and we have our equation here, the KSP, which will be barium ion plus SO4 minus 2 ion. All right, so we have plus S here, plus S there. So what's S times S? S squared. Okay, S squared equals to KSP, which is 1.1 times 10 to the minus 30. All right, now when we mix these two, let's figure out what the final concentration is. So I'm going to write here concentration after mixing. All right, so we have, first we'll do the barium ion. Okay, the barium ion. Okay, so that is 200 ml. Times 0.0040, big M, divided by what's the total volume? 200 plus 600 is 800 mLs. Okay, right? 200 plus 400 is 800 mLs. So what is that on our calculator? 200 times 0.004. I think I should know this, but 0.8, point something 8. .8. Okay. and divided by 800 is 0.001. 0.001 big M. 001 big M. The mils cancel. Yeah. All right, now let's figure out the concentration of SO4 minus 2. And this is going to be 600 mils times 0.0080 big M divided by 800 ml. Okay, the mils cancel. What's 600 times 0.008? Is it 0.48? Oh, 4.8. Okay, whatever. 4.8 divided by 800. 0.006 big M. So I'm going to put that 0.006 here, and I'm going to put, for the barium ion, 0.001 here. And does this equal to KSP? Okay. This is the concentrations after mixing. All right, so 0.001 times 0.006 is 6 times 10 to the minus 6. 1, 2, 3, 4. Yes, I was right for once. 1, 2, 3, 4. 6 times 10 to the minus 6. Okay, it's always good when you can do math in your head. Okay, and what is the KSP? It's 1.1 times 10 to the minus 30. Okay, so they do not equal to one another at all. Okay, so obviously there's a situation here where this reaction, I'll box it here in blue. Okay, this is a situation where this reaction is either going to go this way or it's going to go predominantly that way. Okay, so for that we're going to put Q first and then compare it to KSP. The KSP is given to us at the start of this problem as 1.1 times 10 to the minus 30 for barium sulfate. Q, we just calculated it as 6.0 times 10 to the minus 6. So which is bigger? Okay, Q is bigger. Okay, Q is bigger than KSP. So which way do the alligator jaws point? Which way? They point towards the left. So what side is the left? It's the side that has the solid. Okay, so will a precipitate form? Okay, the answer is yes. Okay, so you mix barium ion at this volume, at this concentration, with sulfate ion at this volume and at this concentration. Yes, yes, that is enough strength and potency to precipitate barium sulfate. Okay. Right, so, this is the type of problem you can expect to see on the exam or the quiz. Right, so we'll put a little star here. So example 8 is something that you guys can look and do at home. This is a little bit more of a difficult problem, so it's not on the test, but you can look over it. And if you can do this problem, then you should be good for the exam. But this type of problem will not be on the exam. It's a little bit higher depth. Okay, but so I would say look over, but concept not on the exam. So let's quickly move over to page 15 here. All right, so look over that problem on page 14, see if you can understand it, see if you can gauge it well, and if you can, then you'll be in good shape for the test. But that particular type of problem will not be on the test. All right, so at the very beginning of chapter 16, we talked about the common ion effect. So the common ion effect basically means anything that suppresses ionization. Okay, it will shift it towards the side away from the ions. Okay, suppress ionization, but in terms of the KSP, it will also suppress solubility. Okay, it will suppress decreases solubility. Yeah. So the common ion will do that. Okay, decreases solubility, which means you would expect to see more on the left-hand side of the equation, which is the solid. Okay, away from ions, basically. Okay, same thing if you're dealing with Ka or Kb types of problems. Okay, we expect to go to the shift with the common ion to the side away from ions. All right. So let us do a problem as before. But this time in part B, we will have a common ion. So let's do this problem. This illustrates the common ion effect and its role in KSP. All right, so let's go here. All right, so calculate the solubility in molarity M of AgBr in A, pure water, and B, 0.00100 molar NaBr. Okay, so first we'll do part A. This is something we've been doing for a couple of days now. I will give you the KSP for AgBr. Okay, the KSP for AgBr. Silver bromide is equal to 7.7 times 10 to the minus 13. Okay, I got it from my textbook, and I'll give that to you on the test. Okay, so that's something you do not memorize, because every sparingly soluble solid will have its own KSP, correct? All right, so let's begin by writing our equation. AgBr is in an equilibrium with silver ion plus Br minus ion. Okay, some of it will go this way, and those that go this way will be plus S and plus S. And then let's plug that into our expression here. KSP is equal to Ag plus and Br minus. Okay, so we're going to calculate the solubility. Okay, how much soluble Ag plus and soluble Br minus is there? So this is S times S, which is S squared, and KSP is 7.7 times 10 to the minus 13. Okay, so S is going to equal to the square root of this. .77 times 10 to the 7, right? 8.77 times 10 to the minus 7. By the way, this is in molar solubility. You want to put in the units in molar. Okay? So this is the solubility of Ag plus. Because it's a 1-to-1 ratio, it's also the solubility of Br minus. So 8.77 times 10 to the minus 7 moles of Ag plus will go back into the water, okay, solution phase, not in this solid phase. and 8.77 times 10 to the minus 7 molar will go in the aqueous phase and not the solid phase for Br minus. So this is something we have done over and over, a couple of times, at least 2 or 3 times. So with that practice, hopefully you're comfortable solving this KSP problem. But part B is a little twist. Okay, so now it's the solvent is not water. The solid is in a solvent that is 0.0010 molar NaBr. Right, so this is part B. Okay, we'll write our same equation. Some of that AgBr will go this way. This will be plus S. This Br will be plus S as before. But what is another source of sodium bromide here? What is the other source of bromide ion? Very good, the common ion. You see this sodium bromide is sodium ion and bromide ion. So what will its concentration be? So there's 2 sources of Br minus. One source of Br minus is this reaction going this way, right? One source of Br minus is this reaction going back. We call that S. The other source of Br minus is where? Okay, as Allison mentioned, it's from the common ion. So we have an S Br minus source from the reaction going this way, and then we have another Br minus source, which is a common ion. So this is going to be S plus 0.010. 0.0010 molar, okay? So this is coming from the common ion. So we do everything as before. The KSP is equal to Ag plus times Br minus. Okay, the Ag plus is S. The Br minus is S plus 0.0010. And that equals KSP, which is 7.7 times 10 to the minus 13. Remember, I'll give you the KSP. Right, so here we're going to do something to make our life a little easier. We will assume S is small. Okay, we will assume S is small. So assuming S is small, that means most of the Br is coming from where? Is it coming from the reaction going this way, or is it coming from the common ion? 7.7 times 10 to the minus 13 means very little, some Br, but very little is coming from the AgBr solid going back. Where is most of the Br coming from? The common ion. So when we assume S is small, S plus 0.0010 will be about 0.0010. So most of the Br minus here is from the 0.0010. Okay, some of the Br minus is from the reaction going here, but we are assuming it's small. And it's a safe assumption because the KSP for this is so small. Okay, it's such a small KSP. All right, so 7.7 times 10 to the minus 13 equals S times 0.0010. And then 7.7 times 10 to the minus 13 divided by 0.0010 is equal to S. Okay, so S is equal to, what is that, 7.7 times 10 to the minus 11? minus 10. Oh, well, can't win them all. 7.7 times 10 to the minus 10. Okay. Right, so doing this, the solubility of Ag plus, which is what we get here, is 7.7 times 10 to the minus 10 molar. And the solubility of Br minus is 7.7 times 10 to the minus 10 plus the 0.0010. And I'd like to submit to you, if you do that on your calculator, you'll still get 0.0010. Okay, because this is so small. 0.001 plus 10 to the minus 10 is still 0.001. So this is the answer. Okay. So in the presence of the common ion, what has happened? At least in the case of the solubility of Ag plus, okay, the solubility has decreased. Okay, 10 to the minus 7, and it went all the way to 10 to the minus 10. Okay, so yes, the common ion will decrease solubility. And your solubility of bromine, was 10 to the minus 10. Most of it is coming from the common ion, okay, which is your solvent, 0.0010 molar sodium bromide. So you can see, compare these two. So I'll write here the common ion, in this case Br minus, decrease the solubility. And that's what the common ion effect will do. It will decrease the solubility. Okay. All right, let's do one more of this type of problem. One more of this type of problem in our last 5 or so minutes to get us some extra practice. Okay. Right, so let's go to page 16. We should wrap up this. Actually, this will be the last page. I'm not going to cover Kf. Okay, I'm not going to cover that, and I'm not going to cover. You don't have to do that in your acid-base sheet. Okay, that lab problem set. So this is the last page for this chapter. All right. Calculate the solubility of silver chloride in 6.5 times 10 to the minus 3 molar silver nitrate solution. All right, so silver chloride is a solid. That's in an equilibrium with silver ion plus Cl minus ion. And the KSP for this is, if we look back, I'll give you the KSP, and it is 1.6 times 10 to the minus 10. Okay, so that's not something you need to know. So the silver nitrate will be AgNO3. Okay, so it's silver ion, which is Ag plus, and nitrate ion, which is NO3 minus. So what is the common ion here? Okay, the common ion is silver. Right. So there's 2 sources of silver here. Okay, there are 2 sources of silver. Okay, so this will be S, one source of silver from the reaction going this way. What will be the second source of silver? From where? Yes, the common ion, which is silver nitrate. So what is its concentration? 6.5 times 10 to the minus 3. Yeah. Okay, and this is just plus S. Okay. So there's two sources of silver, one from the silver nitrate, which is silver ion and nitrate ion, and then the other is from the other second source of silver ion is from this back reaction, this reaction going back. All right. So the KSP is going to equal to Ag plus times Cl minus. Okay. So Ag plus is S plus 0.0065. Cl minus is going to be S. The KSP is 1.6 times 10 to the minus 10. All right, so here what we want to do is we'll assume S is small. Okay, so most of the silver that's coming in this reaction, silver ion coming from this reaction, is actually from the silver nitrate solvent. Okay. So assume S is small, so this means S plus 0.0065 is about 0.0065. Okay. It's a safe assumption to make given that KSP at 1.6 times 10 to the minus 10 would majorly make this reaction stay on the left-hand side. Right, so making that assumption, 1.6 times 10 to the minus 10 is equal to 0.0065 times S. Okay. So S is equal to 1.6 times 10 to the minus 10 divided by 0.0065. 2.5 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, minus 8. Okay. So the answer to this problem is the solubility, don't forget the molar. So the solubility of Cl minus is 2.5 times 10 to the minus 8 molar. The solubility of Ag plus is 2.5 times 10 to the minus 8 molar plus the 0.0065 you get from the common ion. And I'd like to submit to you that this is about the same as 0.0065. Okay, plus 10 to the minus 8 plus 0.0065 is still 0.0065. So this is the answer for that. Okay. If you go back to the previous problem, if you go back a couple of pages to page 13. Okay. Oh. All right, it's asking it for in grams per liter. So I'm going to take this 2.5 times 10 to the minus 8. Okay, so this is going to react with 2.5 times 10 to the minus 8 AgCl. Okay. Molar, which is moles over a liter. Okay, 1 mole of AgCl is how many grams? About 143.31 grams, okay, from our previous problem. So 2.5 times 10 to the minus 8 times 143.31 is about 3.58 times 10 to the 6. Grams over liter. Okay. So you're going to take this and multiply it by the molecular weight to get it in grams over liter. And the solubility of AgCl just in pure water was 0.0018 grams over liter. Okay, this is the problem that we did in page 13. No, sorry. Yes, page 13. And this is the solubility we have in the presence of the common ion in 0.0065 molar AgNO3. And this is in pure water. So the solubility has decreased from 0.0018 to 3.58 times 10 to the minus 6. So the common ion will suppress. It will suppress and remove remove the side away from ions. Okay, suppress ionization. That's what you want to think about when you think about the common ion. It suppresses ionization. It suppresses solubility. Okay, it suppresses the solubility. Okay, so more goes into the solid. Okay, all right. It's 1:51, which means it's time to